Hello and welcome to Motor Doc Podcast, episode 31. Well, as we're weaving through everything we've been up to, I haven't gotten into interviews yet. We'll do that down the road. Now, mind you, I've been doing a lot of podcasts as the interviewee. You'll also find those linked in our newsletter and so on. If you haven't signed up for the newsletter yet, go to motordoc.com, motordocai.io, or empathcms.com, and you can sign up for the podcast there. But in any case, one of the things we've been talking about since the beginning is failure analysis. And in this case, I want to do a quick talk and walk us a little bit through the concepts associated with root cause failure analysis. And as we discuss RCA or RCFA, root cause failure analysis, we're going to explore kind of the tool and the concepts. Now, I'm going to be using a very old version of PROACT, which is a software that was developed by reliability.com and is now an online or cloud-based version, SaaS, meaning software as a service. So you can pay for an annual fee for this one. But there are a variety of other ones as well. I've used this particular one for IEEE papers. I've used it as an expert witness in court cases and so on and so on and so on. It's been very, very handy. But it also brings up an interesting point. Recently, I was involved in something and somebody referred to the root cause of the failure of a motor being a winding short. And I said, well, that's actually not a root cause. That is a fault, but it's a weak point in the system that failed due to some other causes. And as you can see here, there's a few rules to keep on hand. Now, one of the books that I often refer to for root cause failure analysis is a little older as well. I think they've got some newer versions of this one. Root cause analysis, improving performance for bottom line results. Both Bob and Ken Latino were involved with that. They used to be part of the reliability.com organization, and now they are a company called PROACT. And I say that questioningly because everybody talks about how do you actually pronounce it? Where did the name come from? Well, there's a few podcasts out there recently that will help discuss that, both through Upkeep and also through CMMS Radio, two that I listen to quite often. So anyways, let's get back into it. Some facts that we know. For instance, this picture in this slide here from a talk that I do on root cause analysis of machines. This was one while I was putting this presentation together. I think it was 2017 or 18. This is outside a condo next to our place, and we know the people that own this vehicle. And we're walking by and saw this scene. Now, there's a roped-off area. I went up to the rope and took this picture. But there's a lot of people standing there. And everybody saw what was going on, even though they weren't actually present when the incident occurred. But everybody had their own opinion based upon their background, their personal background and knowledge about that vehicle and the owner. So, to put a long story short, all of the different descriptions I heard of what had happened in this incident later turned out to be incorrect. Basically, there was a mechanical failure in this, and somebody put the car in reverse and it went forward instead. And it wasn't the owner of the car, it was her son. Everybody made the assumption that it was the owner because, well, she was being made to park outside because of habits. There's a garage inside the condos, and she wasn't allowed to park in there anymore because of bumps and bangs and so on. So everybody made the assumption based upon that background that she was in the car and drove it off the edge. Well, that turned out to be incorrect according to the investigation. But when we're looking at an incident, what do we understand about it? Well, there's a chain of events that have to occur. And that's why it's important to understand why we want to investigate root cause failure analysis, because the idea to prevent it from happening again is to break the chain of bad. Find a link that will prevent it from happening again and break that link. So some of the rules that go along with it is that it takes 7 to 11 problems to occur before a failure occurs. Well, then why do we have the 5 why concept of root cause failure analysis? Well, those are usually meant for very simple applications that haven't had a significant impact. But if I have a high dollar impact, or one that's considered serious for whatever reason, is important to somebody in the organization, then I need to do a more robust analysis. Why? Because sometimes there's not just one root cause. Sometimes there's a culmination of causes that lead up to one. And we'll refer to this as the failure chain. And if you would watch some of the videos I've put together in the past on things like motion amplification and everything else, you'll see that I used the catchphrase, breaking the chain of bad. And that was identifying the points where you can make a change that will prevent the failures from happening again. Most root cause failure analysis to this day that I run into are limited to the obvious. I've had recently people show me a picture and say, here's a picture of this type of failure. What caused it? Well, there's usually a story behind the actual failure, and they'll tell you the story. But then if I go to the opposite side, if it's a conflicting, if there's conflict involved, I'm going to hear a different story. I'll cover one. I went to a facility and we observed certain things having to do with the failure of equipment that caused fires in the plant. And our testing showed us, our data showed us some very, very specific things were occurring that would lead to that exact type of fault. But somebody in upper management had an axe to grind with another site. So he kept saying, no, it wasn't what we were seeing. It was actually the condition of the materials that were being sent from his rival's site. So that is part of the reason why, when doing an RCFA, while interviews are a good idea, it does several things. One, it gets people involved. Second thing is that those people are bringing their prejudices to play, right? I'm talking about their pre-knowledge, their background, their things that have happened to them in the past, and so on. So all of a sudden, assumptions become real. And I'll tell you, when I've gone and done some of the RCFAs we've done, some that have involved military reliability and life and death situations and costly conditions, industry-wide concerns and everything else, when you interview individuals, you're going to hear a variety of stuff. But when you look at the data, the actual data, and you can apply that data to a number of theories and say, okay, here's so many things that can cause that condition. Where's the evidence that supports each of those, right? So I need to have that evidence. And I have had RCFAs where we've had open conditions, meaning we didn't have an answer. Nobody provided an answer. Nobody provided data that I could point my finger at it, and they said, oh, trust me, it was this, or oh, I observed this in the past. Great. Where's the data? When that data doesn't show up, then you have to leave it open. When it does show up, it's often not what the person claimed. So, and that leads into the next part. The most common problem in root cause failure analysis are the engineers. I am sorry, but engineers have this very, very solid thing about jumping to conclusions, usually closed minds, preconcepts, and you know, I'll say engineering today is not the engineering of old. So I run into this often with certain conditions having to do with electrical systems. You can say, this should not be like this. And, oh, it doesn't cause a problem. Then why is all your equipment blowing up? Well, you know, you don't understand. You don't understand what you're looking at. And you're looking at the data going, yeah, the data exactly says it's this problem. Well, I was taught this, so therefore what you're telling me can't possibly be true. And everything stops right there. So I find this in a lot of cases as well where we're going through an investigation on something that's impacting, say, the entire wind industry. Well, there's something there, and when I look outside and I see the same type of issue but in other industries, and I say, okay, here's how it was solved. Oh, no, we have to do, you know, multiple years of research for something that's usually relatively simple to people in other organizations. Well, test that. Oh, no, we need to study the fault. But then it's limited to a very specific path, whether if the person involved is mechanical, it's studied from a mechanical standpoint, or electrical, it's studied from an electrical standpoint, and nary do the two meet. More importantly is when it comes to the electrical side, because everything becomes a black box as far as everybody's concerned, and they don't see outside of it, and I'm on my soapbox. So let's keep moving forward. So when I'm starting to go through this, there are actually standards related to root cause failure analysis. And one example, before I show some of the actual technical standards, is an IEC 62740, which is called root cause analysis. And it is a standard that guides you through the approach to root cause analysis. You know, what are the processes? What are the methods that are used? When do you apply such and such a method? And so when somebody comes to me and says, oh, we followed a root cause analysis, did you follow a standard? Well, this is one example. There's a few others. But did you follow the standard? A standard? No, we didn't follow a standard. I looked at some pictures and saw this, and so on and so on. Other things for machines and transformers. Okay, now this 1415 was administratively withdrawn, meaning that it just wasn't taken up and redone. But the first, and primarily was because the first section was just a conglomerate of testing methods, and some people had objections and so on and so on. But the back part of it was root cause failure analysis trees. As a matter of fact, a lot of it came from the EPRI reports in this list. So EPRI report 100968, troubleshooting of electric machines. It's actually a root cause analysis process that works along with the next report, which is a set of logic diagrams, which was incorporated into IEEE 1415 as a methodology for saying, if I have this type of problem, here's the possible causes. Okay? And then for transformers, IEEE standard C57.125, which is the guide to failure investigation for transformers. I've used that on mobile transformers and other transformer things. They're similar for switchgear and everything else. Other things that I will refer to include, if I'm looking at shaft breakage and so on, I've got some more in the library, but they weren't here. But, other books, because you want to, if you're looking at something physical, you want to be able to relate that to something that's already published, preferably something that's a recognized publication or that's been referred to or incorporated into consensus standards, or by consensus are pretty accurate. So another one I do for bearings is this one. And this was not a cheap book. I got this from the Vibration Institute, which is a consensus organization. So when I go through here, I can look up different types of fault issues let's see one that'll come into play here in a minute. But I can go through here and identify different kinds of conditions, right? So, let's just say ineffective lubrication. Here's a couple of conditions that can occur with the bearings. So identifying the types of issues I'm running into and then taking a look and saying, okay, this is actually, one of the possible causes. What conditions surround it? So, for instance, in a video I'm going to show you in a minute, somebody said, oh, it was improper lubrication because that particular type of failure is associated with it. But there was plenty of lubrication and it hadn't lost the oil, so that was not an accurate description. Another one from professional organizations include a consensus standard for electric motors called root cause failure analysis. There's another addition to this now, but this is the edition I'd purchased some time ago. If there's updates and so on, fine. I'll also go to IEEE Explore for electrical conditions and things specific to certain types of machines and other, professional bodies like that. I don't necessarily go to, the web analysis. And I'm cautious a little bit about going, if I'm looking at bearing stuff, somebody suggests, go to the, so-and-so manufacturer's bearing guide for failure. Well, why don't I do that? Well, because they always say it's lubrication. It's always lubrication. Unless it's electrical. It's always something other than some condition going on. So the method I was talking about is the PROACT method, and we're going to go through the older version of that, and this is the version of software that I have. So it's still on something very ancient called CD for those of the younger generation. So I had to find a CD that would connect to to this laptop so I could load it up. And then, of course, there's licensing things and so on with it. So, but anyways, that stands for preserving the evidence. Well, step one, preserve the data. If I go in and I do stuff and I damage the evidence, then I've lost that evidence. But that evidence could be things like data. So I had one recently where they wanted us to do an RCFA on a machine. We were getting involved in an RCFA. The idea was that a particular incident occurred in November. And they said, so they discovered it in November and it had just happened and everything else. Well, the data they had provided, I'm looking at the actual operating data for the machine, vibration, temperature, and everything else, and I'm going, no, it actually happened in April 28th at this exact time. And they're going, oh, no, you don't understand what you're talking about. This is what we observed. There's no possible way it happened then. Well, let's see. It involved the fan inside the machine. The temperature went up and the vibration went up. And it remained constantly at that level all the way up until you discovered it, which means that it had existed that whole time. No other incidences occurred on that date and time that it was discovered. And then all the other stuff occurred afterwards. And all the evidence that I'm looking at, all the actual data that was gathered by the equipment shows no changes during that entire time. That means that most likely the condition is this. And you'll notice I never say exactly 100% because you can't. You can't. You're not living in it. You're going back and recreating something using the evidence around it. And there's very rarely is there something called a smoking gun, because if it's there and it's a smoking gun and you don't have evidence, just an observation, then anything could have happened, right? The human mind plays tricks. If I come in and I'm predisposed about some type of incident surrounding some type of concept that I have, the world I'm in, and then somebody else comes along and they're looking the exact same data, but their world is this here, and you're communicating. That communication, you might be saying words that the other group is understanding, but they're interpreting it based upon their training and background, and you're communicating based on your training and background. It's often, if not always, misinterpreted on the other side. So let's get into the incident at hand. So this one here, if you've seen it, I call it Motor Go Boom, and you can't see the top of the page, but it is a test that was performed after field testing was performed, in which electrical signature analysis using the empath identified a bunch of conditions. And we went, wow, how is this motor even running? And the vibration guys from there, because they were doing continuous vibration monitoring, said, what are you talking about? We don't see a problem. And basically they were seeing it, but the levels were so incredibly low that they said, there's no issue here. We don't understand why you're concerned. Well, maybe it's because there's a problem here. And it's like back and forth. So they said, well, we're gonna show you, and we're gonna take it out. We're gonna put it on a test bench, and we're gonna run the motor. And the repair shop involved was the one using ESA. And the engineers involved said, there is nothing wrong with this motor. We'll pull it out. We'll test it on the test bench. So so that's a headache. Motor's going to blow up. Well, obviously there's a bearing issue. You saw that, but you can also see there's a brush on there to prevent electrical discharge in the bearing. I don't know how this is all going to sound when we do it. That was the winding failing. There was a flash there out of the connection box, and the technician just had to turn it off afterwards because it tried to continue to run. That's the tech who was running the test. I blurred the top end just so I don't have faces in there. The legs and the black pants, that's me. The empath was there. And then we pull it off, and you can see that's all copper. The big chunk blown out of the winding. This is the opposite drive end. Somebody said, oh, that's obviously lubrication. It wasn't. There was plenty of lubrication present. That's the outer race of it. This is the drive end. What was particularly interesting was this one here. This is electrical fluting, meaning electrical discharge, on the drive end where the shaft brush was located. So that leads us into an RCFA. What could possibly have caused that? Now, this is the PROACT suite. We're going to go ahead. I've already put some stuff in there. So this is motor dock. Let's get into, we'll create a customer. So this is how I use it. So we're going to call this repair shop. Okay, so we now have repair shop. That's up out of the way here. Can't see it. Here, let's get this down here for a second. There's repair shop. When I come in here, I say, okay, let's get the information together. We're going to add the equipment, and we're going to say electric motor. Okay, so we've got the electric motor sitting there, and we'll just kind of end there. Let's get into an actual RCFA. So here's the fun part. There is no study. Older version of the software, I'm probably going to have to restart it, aren't I? Okay, so so here we go. So we're going to we have an analysis name, the property. So we're going to say new analysis. It's going to bring some stuff up. Motor go boom. So now at this point, I'm going to describe the situation. We're not into identifying what's happened yet. That's probably the most difficult part. What are we actually investigating? Okay, there's a lot of things associated with that machine. So we're going to say the analysis description is going to be determine. I'm sorry. We need to discuss the thing. So an electric motor on a belted fan. inline fan was detected as having mechanical bearing, winding defect, and static eccentricity, as well as belt and sheave signatures above at above minus 65 dB. The motor had an existing machine learning based vibration program with a single vibration accelerometer mounted on the stator housing. That's important to note, by the way. The actual, if you saw the little silver piece sticking up from the motor, it was not above the bearing on the end shield. It was actually back off, and it was in a mass of soft material, kind of glued in place. We're going to say this is going to be, we're just going to call it a mechanical in this case. But it can be more complex. I don't know the dollars involved. We're going to ignore that part. I very rarely use that. Okay, so we're going to call this in the repair shop. And there's other things that we can put in there. Equipment type, electric motor, and then I didn't put anything else there, so we're going to just keep that. Cross-functional team doing the analysis. Now, mind you, you might have, and this is a really interesting point. You're going to have a person who runs the RCFA. Now, when I listen to a lot of consulting firms that don't have a lot of technical background and they run into something like this, they're always the ones who publish articles or say, you need to bring in somebody who actually doesn't understand what they're looking at, blah, 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 blah. And you can probably pick up from my voice that I'm saying that's absolute BS. You actually want somebody who understands what's real and what is not, and should have a background in the type of conditions going on, but should not have a direct tie. So, for instance, if I'm brought in to look at an electric motor root cause failure analysis, it's because I have a background in electric motors, but I don't have a horse in the race. Meaning that I don't have I'm not responsible for that machine, or I'm not tied to what the final results are. Okay, and as an RCFA, when I do RCFAs as a specialist, I'm brought in. Believe me, I get constant calls, and I enjoy those calls because I'll get constant calls from those who are directly affected by it, trying to aim me in a specific direction, trying to manipulate the evaluation. The minute I have somebody manipulating the evaluation, I know I'm on the right track. And that's a big secret. Keep your mouth shut as the observer. Watch what's going on. We're not supposed to focus on people, and you're not looking for blame, but people always take it as being blamed. So no one will be disciplined for honest mistakes. And notice that, for honest mistakes. And I have had some of the conditions where I've gone in to do an analysis, to do an RCFA, and people have done deliberate things. And it becomes really obvious when that occurs. And some of those things are not good, not good at all. So here's the charter. We're going to find out why something went boom, and we're going to find, we're going to look at both management decisions and everything else that goes on. So any comments can go here. This is just a sample charter. We're going to skip all that. We're going to get to the fun stuff. Who would you like to be on the team? So you add the team. In this case, it's just going to be just me. And we're just going to say it's starting in, today, and it's going until whenever, right? So today is when it's starting, and then it's going to end in July. So here we go. We now have set up the stuff for the RCFA. Now, the first part is preserving. So what data do I have available? Now, I'll add the record. So, it'd be things like, paper, right? Paper really means ESA data. Okay. So, keep segregated. This would be right off of the software. So the repair shop had provided that to me. So add another one, vibration data. Have client provide vibe data or data associated. And then here, this is interesting because this is actually what happened. Vibe company identified that their data is proprietary and would not provide it. Basically, it was a cloud-based system, and just a note, customer does not own the data. So this is really important, especially when dealing with some of the modern IoT systems. And this is why I get concerned when I hear that a company says, no, you don't own the data. We're collecting the data and we're doing the analytics for you, but we own the data. And then video of failure, preserve, okay, and then the unedited. I'm doing this quickly at this point. Tear down images and measurements. Okay, so we did all test reports and images. Okay, so let's just keep it at that for this purpose. Otherwise, we're going to go on because these are not short. These are not something that you're going to knock out in 5 minutes. Next part is order. Okay, so this is the data. Here's the charter and everything else. We're going to save everything, and we're going to get into the fun part. Now, the fun part involves this. First thing I'm going to need to do is say, okay, we're going to analyze it. And where's my thing? Here it is. And we're going to create, okay, what is the event we're investigating? Are we investigating the machine failure? Or are we investigating whether or not, why did the vibration system not detect the problem? Or are we investigating all of it? So what is the actual event that we're investigating? And this can be a big point of contention. So we know the equipment failed. We know that it didn't trip any alarms with the anomaly detection system set up as vibration analysis, right? So the anomaly detection didn't flag anybody to go do the work that we're aware of. I mean, so this is what we were told. So really, we're looking at both. So, so we're going to just make a statement. Electric motor driving inline fan with belts failed or I'm sorry, yeah, failed. So it functionally, we'll just call it functionally failed. The next one of these presentations I'm going to do is on reliability centered maintenance. We'll discuss what functionally failed is at that point. So I say, okay, it's functionally failed. Well, what could cause it to functionally fail? Okay, so we're going to say mechanically failed, and we're going to say electrically failed. So we're just going to keep it at 2 points. So now we have the beginning of our tree. Okay, so under mechanical failure, now we've got to come up with hypotheses, right? So, and we can drill down further. But let's just, there's ways of adding in additional modes. So let's go ahead and say, we're just going to say bearing failure. Okay, and just from our observations, we're going to say pretty high, so confidence level of 5 out of 5. Bearing, bearings failed. Bearings failed for some reason resulting in noise. So I'm skipping a couple of steps here, but we're just going to say that we're going to do that. So that's a hypothesis. Another hypothesis might be shaft failure. That the shaft failed between the output and the rotor. Okay, maybe it's a cracked shaft, maybe it's loose in the rotor. Okay, so we'll give that. Well, that's not usually that common. So we'll say, because I'm not really seeing anything along those lines, but I'll give it a possibility. And I've done this before in a couple. I've gone in and I've said, okay, go on and we take a look at, say, a seal failure, and I've got a long line of conditions that could cause a seal failure. And I remember saying, you know what, there's some changes with the lubrication, or there's changes in the material being used, and there's changes in the lubrication. Why don't we just do a quick check on the oil? So I added one. It was oil, and we're looking at a good solid type of seal material. And what ends up happening is we discover that the tear sheet for that oil says specifically, whatever you do, don't use Viton. And it was a Viton seal. Matter of fact, all of the gaskets and seals had been converted to Viton because everybody thought Viton was impenetrable to everything. Well, as a matter of fact, it turns out for one of the additives in that particular oil, it was aggressively attacked and turned gummy and sticky and came apart. So it turns out instead, Buna N turned out to be the perfect material to use, which, by the way, was an order of magnitude of 10 times, meaning it was 1/10 the cost of the Viton. But we didn't discover that. It wasn't even a consideration until we just happened to add it. So let's go back, and I'm going to skip this part up here for time's sake, and let's just hit the bearing failure. Now, if you saw the two types of bearing, let's say we'll come in here and we'll say, okay, bearing failure, we're going to say there's a verification method, and we'll add one. The verification method is visual inspection of the drive end bearing. Outcome, drive end bearing showed signs of fluting on the outer race. Okay, so we now know, based on the picture, and we could do a file link to that picture if we've got everything in one folder, that kind of thing, so that when we print out the final report, all of that's included, right? But for this case, we're not going to do that. And we can put in the number of hours involved and so on if we want to keep track of costs. But that's specific to that. We're not concentrating on that part right now. So drive end bearing showed sign of fluting in the outer race, noted that it also had a shaft brush. Okay, so that was interesting in that it had a shaft brush, and we found something completely unexpected. It was under 100 horsepower. So we now know that we have a condition, right? So the question is, do we have a hypothesis that goes along with that condition? Shaft brush not in contact. Okay. Shaft brush not in contact allowed current flow through the bearing. By the way, I speak through this in case anybody's listening to the audio version. So we'll say, okay, that's a pretty high probability of that. We can take our guesses here. The next one, now we can have, what we could end up doing here, in fact, is we could say, okay, bearing failure, and then we split it into drive end bearing and opposite drive end bearing, and then perform the analysis continuing down into a much broader tree. And that's normally what I would do. So, but for purposes of what we're doing right now is I just want to show you the process of thinking through this. This is referred to, by the way, as critical thinking. Something we seem to be lacking. And it's one of the reasons during the past few years, starting with 2020, that there was a lot of contention going on because people who were trained in critical thinking were questioning everything, and the general populace, by mob rule, was basically saying, you can't do that, you must follow the science. And the people who were involved in science were going, wait a minute, we have to do critical thinking, that's science. No, it isn't. This is science. This is whatever we say is science. This is a problem. And I run into it constantly in the field, especially through people, when I'm doing an investigation, especially by people that should know better, they will usually throw emotion into their analysis. And the minute they throw emotion into the analysis, it's done. There's no point in going on, right? And I've walked away from RCFA projects because, you'll have somebody so invested in that being the conclusion that they will do some really, really vile things and use name calling and everything else to people that have any different opinion than they do. And I just don't deal with it anymore. I walk away. If that company wants to have that kind of individual, that toxic individual in their organization, there's one of their root causes. And when you start down that path, it's not something I'm particularly interested in. So let's say next hypothesis, high ground currents. Okay, so people don't realize that. Okay, so I'll talk this out real quick. High ground potential voltage or currents with harmonic content or noise will generally discharge through the brush in parallel with the bearing. Okay, so I'll get into this discussion real quick. So we did inspect this one. and we're going to say, I would go in here and say, okay, verify brush in contact with visual inspection and measurement. Okay, outcome, low ohm value with multimeter, and visually in contact. Okay, so what I'll do if I say visually in contact, I'll always have a picture along with that. You'll have the measurement either signed by somebody or written down or saved, or an image of that as well. So I like pictures, a lot of pictures. People are very visual. So that means I can come over here and say that is not one of the causes. Now, high ground current. Okay, verification measure would be take measurements of ground in voltage and current, using ESA to view values in RMS and waveforms. Okay, this is really important that you see what does the waveform look like. I mean, if it's a nice sinusoidal thing, it's probably not going to be causing problems. But if it's very jittery and I have a lot of harmonic content in it, well, here's what happens. And I hit different frequencies. Some of those frequencies do things I don't expect, like not go through the ground brush and instead go through the bearing. But also what happens, and most people don't realize this, is that just because I put a shaft brush there, if I don't insulate the bearing, I have a capacitance and resistive circuit on that side, and I have a resistor, because I'm not 0 ohms. In parallel with it, all I've changed is the RCL circuit, meaning that I still have discharge happening in the bearing, but at a much lower value. Now, if I put a dielectric material on there, I'll adjust it even further and I'll reduce it, but mostly what I want to do is put an actual insulator with the bearing, such as a ceramic. So I might have a ceramic ball, I might have ceramic coating on the outer race. I don't like the inner race because ceramics don't expand or contract, and the shaft of a motor tends to expand and contract a fair amount. I have seen cases where people put ceramic on the inner race of the motor of the bearing. Well, that's because the tooling from the bearing manufacturer is less expensive. They can use that across many things. So they'll put a coating on the inner race, which keeps it cheaper, put it on, and then when it doesn't expand and contract, they'll start eating away at the material on the shaft. Or worse, it will expand and will fracture that ceramic, meaning that I have a fine point then for discharge, which changes everything, makes it much worse. We've run into this in wind, and we've run into it in other conditions. And just because, by the way, the bearing might be on the driven component or elsewhere in the system, and I'll talk about this in a few weeks about some of what we looked at in mapping of a wind turbine nacelle to detect main bearing failures, right? So when we do that, we come to the conclusion that, because we haven't done the mapping yet. So what we're going to do is this. We're going to say this is a possibility, high probability, but I don't have a conclusion yet. Okay, electrically failed. I'll follow this down the same path, and in the end, I'll say, okay, shaft failure. Okay, let's just say I'm going to open this up because there was something there. Let's create one. Check for shaft fractures and spacing between the rotor and shaft. Okay, so basically was on one side or the other loose, and I can do a number of different tests. So use visual and hammer test. Okay, so appears to be slightly loose on the failed end of the stator. Yeah, on as the shaft enters the opposite drive end of the rotor. Okay, and of course pictures and everything else associated with it. So I say, yep, this is definitely part of the issue. And what I would do here is say, okay, is it a latent? Is it a human problem? Is it a physical root? Actually, I'm going to say it's a latent root, meaning that that machine had run for a while and there was a probability. Now, when I get into human error and stuff like that, which make up a small portion, or actually make up a large portion of things that go wrong, we'll get into that later. I mean, one condition I was looking at recently in RCFA, it had to do with harmonic content, and it was destroying a machine. And when we went back, because it was a special order machine, it turns out that somebody along the way neglected to specify the operating environment included harmonic content. So the OEM just didn't design around it. There's things they could have done to improve the survivability of the machine in those environments. At the same time, why wouldn't you build that in and say, hey, by the way, this is something we're going to do, and use that as a sales point? Nobody did. So the end result was, a lot of partial discharge on a high voltage machine. So we could go into stories like that, but then I would take up any chance of using those in future podcasts or not using those in future podcasts. What's kind of cool about an RCFA is the process of the RCFA is also used in reliability-centered maintenance, and that's going to be our subject for next week. So with that, I am going to say thank you and adieu. We will return to RCFA later on. I just wanted to give you a quick introduction into the process and one of the tools that I use. So thank you again, and have a great day.